So today we are going to take a bit the shift out. We still have the multi-phase flow part, okay? I prefer to leave that for later, when we see what kind of things you have to take into account when computing the production profile and you have, the three phases. So far, we have dealt with some simplified dry gas, undersaturated oil, but in most cases you have all phases. If it's a gas field, you have some condensate, you have some water, and if it's an oil field, you have gas coming out of solution and you have water. So you have to be able to tackle that problem. So we are not going to solve, that requires to have a simulator. As I mentioned, we might do that towards the end of the course if there is time. But I just want to give you, I will give you the fundamentals such that you understand. Basically, you have to discretize. Okay? You cannot have just one unique equation for the tubing, one unique equation for the pipeline. You have to discretize. And that requires that you need to do, you cannot solve it with one BBA function in Excel, but you have to use some more advanced programming. Okay? And it does some changes to the profile. But if you know how to tackle the case, the simple case, you will know how to solve the more complicated case. Okay? If you remember and you keep the fundamentals, okay, this equilibrium calculation. So what I want to go today is that basically we have a lot of uncertainty. Okay? We have uncertainty in the operational phase also. We are not sure about our system, we're not sure about the size, we're not sure about many things, but we have a lot of uncertainty in the field planning phase. And essentially, so that's especially big during the development phase. Okay, and essentially you have done some exploration, some seismic, but you haven't been producing your field for a time. Okay, when you produce a field, you get a lot of useful information. You can do well testing, you can do rate testing, you can do many things that can help you to confirm or to take away some of the assumptions you took on the field. Okay? So it's very important simply to try to quantify in any value we provide. Okay, either if it's we're calculating production profile, we're calculating NPV, we're calculating these values over which we take decisions. We have to be able to quantify the uncertainty of that number. How certain we are if we want a plateau of, for example, 100,000 barrels per day. How certain are we about the plateau end? Okay, is it 100% sure? Is it 90% sure? How sure we are? So how you already had I think you had an exercise or not, where you had to make a tornado chart. Okay, that's a way to account for uncertainty. Okay, a very simple way. So one way that we already covered, okay, is by this principle, which is ceteris paribus. Okay, which means all others same. Basically, I keep everything constant and I change one. Okay, then I keep everything constant and I change another one. Okay, and that typically we say that's sensitivity analysis. Okay. Where we change one at a time and we try to map how the variable over which I will take my decision, or this key performance indicator, how is it affected by the variation. So the main purpose of here, the purpose is to evaluate how the KPI, okay, that's a key performance indicator, varies with the input. Okay, and that input typically, if it's cost, it might be the volumes in place, might be all kind of things that we are not 100% sure. Now, that's not the best way, and that's a very simplistic way, but that's not the best way to deal with uncertainty. Okay, you're going to see right now, but it's not the best way, because it can be that also all the other variables might also change. Okay, they might not be, if you have a process where you have certain variables, variable 1, variable 2, okay, and you have some function or some process, and finally you get a result. You cannot guarantee that simply by taking the extreme of one variable with the average value of that variable that you will be able to quantify the whole variation of the result. It's not as simple as that. Okay? So I think we can start with an example. I like to make this part because it's a bit it requires some abstraction. So I think it's better if we start with a very tangible example of something we have to make during the field development process. Okay? In the field development process, we have to make a probabilistic reserve estimation. Okay? Simply, we have to provide how much oil, how much water, how much gas we have in place, and what is the distribution, where is the probability of each one of these numbers. Okay, and let's take for a very simple case. Okay, let's assuming that it's like almost like a box type reservoir. Okay, box shaped or cylinder shape or any shape you want. So to calculate that n, okay, we're going to use an equation, and that equation we say is n, okay, the initial oil in place or oil originally in place, okay, will be the rock volume, the volume that I have, times the porosity from all of that rock volume. The only thing that I care about is the space filled by the space in between the pores, okay, which that's why I have the porosity. Okay, that's going to give me this guy here is giving me this space, right? And then if I not only have this oil, or I don't have only gas, but I have also water, for example. Okay, so you typically have some other substances, oil, gas, and water. So for example, water surrounding the rock. If it's undersaturated, I might have something like that, with the oil simply in between. Okay. So for that, to finding exactly the place occupied by the oil, I multiply it by the saturation of the oil that I have on that rock. Then I know that volume that I have is not 100% clean, is not 100% pure, the bearing rock, but it has some, some dirtiness, some slabs where I have shale. Okay, so I use a factor called net to gross. Let's put it here, net to gross. Okay, that simply put, we had that in a presentation, I think was a few weeks when we talked about I think was that was Visund, I think it was your group, right? Okay, so you take on the whole, you make a logging. Okay, you take an instrument, you take it will take measurements, and then from there you determine what is filled with shale, what is filled with the bearing rock, hydrocarbon bearing rock. Okay, and one way to find that net to gross is basically to say this H1, here you have H2, here you have H3, H4, and H5. So simply you sum H1 plus H2 plus H3 plus H5 divided by the total H. Okay. Simply I try to find out where from all of that volume where the hydrocarbon might be placed. Okay? That is a very simplistic way to calculate N, but it's just to bring how do you account for uncertainty. Okay. What are we missing on this equation? The BO, the formation oil volume factor, BO. Okay. Now, if I had simply, just one number for each one of them, then I have simply one output. I'm sure the BO has this number, I know the porosity has this number, and then I simply calculate a number, right? But that's not how life goes. Typically I have variations. There are on all variables in that formula. Okay. And the way we account for that variation is we use typically a probability distribution. Okay, so you should use a probability distribution okay. And where that distribution comes from, it depends a bit how much information you have. Okay, for example, let's say you made, let's say you're going to get an exercise tomorrow, okay, a class exercise, and there we are going to work with the values for the Hebron field. Okay, they have done, for example, for phi, and an example I'm going to put here. For the porosity, so 2,287 core samples taken from exploration wells. Okay, so that will be your population. If you take all of that sampling from all the reservoir, from all of that rock, and then you try simply to characterize how the variation of these phi. And the way it is done is simply I start to count. Okay, I have what you are going to get in the Excel file is the number of sample number, and the measured value of porosity. Okay. Then the next step, you have to find some representative, because these numbers, they will be in fractions. Okay, they will have porosity of, for example, 1832 or 1921. So you have to find a way to group all of those. So you say, for example, the porosity goes from a minimum to a maximum that you can determine. Okay, you can determine maximum and minimum on that column, and then you decide on a splitting. You decide if you're going to use 10 points in between, 5 points, 20 points. Okay, so you use something bigger than phi mean, phi 1, phi 2. Let's say we use 3. Okay, we use here 5. Now you start to go one by one and see where that one falls. Okay, and one way to do that is maybe let's change it. Let's put it on like a scale, something like that. Okay, so you define exactly the mid of the interval. Okay, well, actually it will be here. So you will have an interval number 1, 2, 3, 4, and 5. Okay, so you come one by one and you start counting. Where does that number belongs? Okay, it belongs on the interval 1. Then you go to the second. Where does it belong? To the interval 2. And you count how many occurrences that interval had. It doesn't matter, it doesn't have exactly that value, doesn't have exactly that number. It has to be around, close enough to group it. Okay? Then after you do that, okay, you will have, for example, a lot of, samples fall here, fail in here. Okay, let's say the other fell here. That's the number of samples. Okay, then here, then here, then here. To make it to calculate the probability of occurrence, you have simply to divide that number of samples of that bean by the total number of samples. So that means from your what happened here? From your population that you had, let's say of 2, you're going to get these 2,287 samples. You had 50% of them had this porosity. 20% had this porosity. 10% had this porosity, and so forth. Okay, and that's so that's what we call a P, the probability distribution function. And we typically use a bar chart for that, and we simply have phi and simply assign, you use like a bar type chart. For example, let's say it gives you that, and the probability will be the number of samples for bean I, okay, for that particular porosity, or let's call it for porosity phi I, divided by n total. Okay, so far easy peasy, right? Now the problem is that we are not sure. It might be we have a much bigger reservoir that we managed to drill, okay, that we managed to explore. So we have to find a way if what will be the distribution. That's the distribution of something I measure. Okay, something I know, a population I know. Now you want to extend that population to the whole field. Does it apply to the whole reservoir? I'm not 100% sure, but I hope maybe it applies. If I take a lot of samples, okay, let's say I'm looking at my whole reservoir, and I took a few samples, okay, maybe if the probability distribution that I compute with only these 3 probably won't represent the whole field. But if I take a lot of samples, if I'm able to make a lot of drilling everywhere, I can calculate the PDF, probability distribution function. Okay. And then I can assume that any place where I drill, or the rest of the reservoir has exactly the same distribution. Okay, so it's like two different concepts. One of them is the one I can measure, for which I have data. Okay, that's the frequency distribution. But the other thing is to make assumption of something that I haven't measured yet, and that becomes probability distribution. Okay, so in this case, if I have enough samples, I can say that the PDF represents the whole field. Okay. Now so that's the way, if we present it here, that's a discrete, okay? Discrete probability distribution function. That means that I have beans, and each one of the beans, they have a number, okay? But I could also make it, let's say I have no measurements, okay? I cannot say anything. I have no idea how, let's say, saturation can be. I have no idea. I haven't done a lot of measurements. I just made 2 measurements, okay? If I haven't made any measurements, okay? For example, what will you do in that case? How will you characterize? How will you make the PDF of that value? Okay, let's say, for example, what okay, let's say of porosity. Okay, the same. If I haven't made any measurements of porosity, okay, how will you characterize now? What kind of PDF are you going to make for that porosity? You say, well, I'm not sure, right? I know maybe the porosity can be in that area, in the North Sea, from what number to what number? Who here we have in that likes petrophysics or reservoir engineering? Okay, you say, for example, 5% all the way maybe to 30%. But you have no idea. Is that correct or too high? Okay, that's fine. So I have no idea how they are. I know that for each area, if I have measurements, I will be able to find a particular distribution. But I have here no idea. I haven't made any drilling. I haven't made anything. So I say, well, for very roughly speaking, you can find any value from 0.3, from 0.05 to 0.3. And all of them are going to have exactly the same probability of occurrence. I have no idea which one is preferred. Okay. While here you see that the range maybe is narrower. Okay, and you have one particular probability for each number. Okay, which in this case looks very roughly uniform. Okay. But here note something. Here the distribution is continuous. Okay. That means that you can pick any number between 0.5 and 0.3, and then you can find its probability. Okay? Now, let's do one more example, okay? If I have let's say I have a consultant, okay, in my company that has some experience with the area, okay? He might say, for example, to make this approximation better, he might say, well, you can go on that area from a minimum to a maximum, but usually in that region we have one value which is the most frequent. That area for that particular block in the Barents Sea, in the Norwegian Sea, usually you have that number, which is more likely. Okay. So there are all kind of distributions. You have this uniform distribution. You're going to work with that distribution. That's the triangular distribution. Okay. You also have log normal distribution. Okay, something like that, where you have some more data. Okay, that's a variable, and that's a PDF. You have also the normal distribution, the standard distribution, and you have all kind of distribution, okay, that you can use. And typically each variable, if they have done some measurements or they have some experience on the area, they know which distribution fits it best. But if you have no idea, you go for the simple. Okay, simply everything have no idea. Everything has the same distribution. If you have some more information, you use something more sophisticated. If you have even more information, then you start making something, you know, more complex. Okay, looks at, for example, log normal or normal distribution. So for our example that we are making, right, we have this n, okay, that depends on all of these factors: VR, porosity, saturation, net to gross, and BO. So we can visualize that's simply, for our case, is an expression, okay, simply a mathematical expression. But it can be in reality any, if you think about it, you can use Petrel to make that calculation. You can use any software. So that's can be a function, can be a software, can be a tool, whatever. Okay? But you use that input, which is VR, for example. And VR, you're going to have a distribution. Remember, if you don't know anything, simply uniform, PDF. Porosity, exactly the same. Maybe I know a bit more information about porosity due to exploration drilling, so I do something like that. Then SO, saturation of oil. Maybe I have even more information. I do like that. Net to gross, maybe I have no idea, so again I make something like that. Okay. And the last one will be BO. Let's say it's also rectangular. Now the intention is that you have, and remember, they might be based on data that you measure, or simply might be based on experience. You know, I call this the smart consultant. He always has an answer for everything, so he tells you use this with these numbers. Okay, whispers you, and you have to pay a lot of money. Okay, or measurement, or simply assuming. Okay, simply assumption. There are some variables that simply I just have to assume, no other choice. So what would you expect here when you use your software, Excel, function, simply math? What do you expect to obtain here for n? The same. Okay, that's really what you're looking for. That number is something that you need for in the business identification case. Okay, that's the first number your manager is going to ask you for. You need it also for the PDO. Okay, you need it also for the whole development process. We have to know what is the size that you have there. Okay, so you wish also that if you have that input, you also wish to have something like that. That tells you, well, that's the average, the mean, okay, or that's the mode, or that's, and also that's the whole extent of the variation of that parameter. Okay, not to have just simply one, but just to have the whole range of occurrences and which one is the most likely to happen. Okay, if you have here that plot, for example, you might say, well, that is really, this number is the most likely. I can still get here this number, and I can still get this number, but the most likely, if you consider statistics, is this one here. Okay, now you're going to obtain that distribution. Due to that distribution is affected by the output distribution, is affected by the input, the distribution of the input parameters, of the input. Okay, what kind of distribution you have here. And if you will see, if you, let's say all of them are uniform, that doesn't tell you this one will be uniform, because that's not the only thing affecting this distribution. It's also the function, the type of function. Okay, depending what do you have inside. In our case, we have an equation which is continuous, so probably you will see will give you something like that. Okay, but if you have, for example, some logic inside, if b is below certain number, just simply put 0. Okay, so in that case, the distribution might not look like that anymore. It will have a gap, or it will be missing part of it. Okay, so keep that in mind. It's affected by both things. What do you have at the input, and what do you have at the output? So how to calculate the PDF of the output? And there are different methods people use. Okay, I'm going to just show you two alternatives that we use for this particular problem. So you have to use something called a sampling method. Okay, you have to use as a probabilistic type method, and a method such that the idea is that you sample. It's like, let's make it, maybe you have a function. Okay, let's say you have two variables only, x and y, and set. This will be f set is x and y, and you have that range of variation, right? Let's say you know that will be your porosity, can be from 5 to 30%. That will be your, I don't know, volume of the rock, can be from some millions to some billions, okay, cubic meter. And you want to find out, you know, the end, okay? So you want to exactly know, for example, if we have a function like that, okay, let's say that that's your function. That's really what you want to know, okay, how that function is going to change with x and y. Okay, so one method that is typically used is simply you perform a random sampling. Okay, you simply start combining. You have x and y, and you simply start combining them randomly. Okay, and for each number you're evaluating this function set. Okay, so you make combinations x1, y1, and you calculate set. You make x1, for example, y2, you calculate set 1, 2, and so forth. And you make a lot of evaluations, okay, to try to define how this function set how does it look like, to try to determine how the function set looks like. Okay, and this method is what we call Monte Carlo. Okay, this is called Monte Carlo, and it was actually proposed by two engineers from the Los Alamos, I think they were physicists, from Los Alamos laboratory, and they say that actually one of them, I think Ulam, liked to go gambling, so he was trying to find a solution how to beat the casino. So, but maybe that's only gossip, I don't know. Okay, and basically the procedure is as follows. Okay, to calculate the PDF of the output. Okay, you have first to assume a random number, for the input, and you have to do that for each variable you have. For each variable. Okay, then you have to run the simulation, okay, or calculate output, and then you have to compute, then you have to register or save or store the output. Okay, and then you repeat from the beginning, and this you repeat for n times. And this is usually a big number. If you have a lot of variables, like in this case, you can imagine, right? If you want to map that function, you have to make a lot of combinations. Okay, you have to make, let's say, for that area, maybe at least 100, so you can get a good overview of your. After you're done with that, okay, then you come and apply a frequency analysis on the output. That means exactly what we have discussed here, that you have the collection of points, you have all cases, you divide by beans, and then you start counting where it goes, each number. Is it go here, or it goes here, or it goes here? Okay? And finally, you obtain your distribution. Okay? And then obtain the PDF, okay, the probability distribution function. Now it comes the question, how many n times I have to make that run? Okay, for how many simulations I have to make? How many Monte Carlo simulations I have to make? And basically the way is that n should be chosen such as the resulting PDF doesn't change significantly. Okay? So you choose that number such that the resulting this PDF doesn't change significantly. Okay, what you obtain here. And remember, it will be discrete, so you're going to have something like that. Okay, that will be, in our case, is n, and that is PDF. Okay, it's already 1, so let's take a break. Okay, 15 minutes, and then we continue. Yes. So, but just be careful. One way we do the sampling, okay? The sampling is done, the random sampling is typically done on what we call the CDF, okay? The cumulative probability function, CPF. Okay, and you're going to see now why we do that. But basically, if you have, let's say we have that uniform PDF that simply was from, let's call it x1 to x2, or x min to x max. Okay, simply the CPF is the integral of that function. Okay, and you can make the integral in two ways. You can make it on that direction, okay, and that represents the cumulative probability. So we say there is, and this goes all the way from 0 to 1. Okay? So this chart means that you have there is 100% probability that you will have a value of x that will be lower, equal or lower than x2, which makes sense. Okay, x2 is the biggest, so everything, if I pick any number, will be equal or less than that, 100% sure. Okay, and then I do the same for another. Here, if for example it's 50%, so there is 50% probability that my x number will be equal to that or lower. Okay, and I can make it like that. If you make it on the triangular distribution, and I have here the mode, okay, it gives you surprisingly something like, okay, something like this. And the CPF, remember, always goes from 0 to 1. The integral under the area under the integral is always 1, 100% probability. Okay? So the way we assume the random number to be, you know, because it's more consistent that way, we like to take usually a random number between 0 and 1 in the CPF, such that we start any random number, and then from there we go on the CPF curve, and then we read the number, the value. Okay? Because then you don't need the random generator, can be simply from 0 to 1 number generator, and then I have that equation and I find the value of the variables. Okay? The justification is that if I take random sampling, eventually it will become very uniform between 0 and 1. Okay? And then I will be able to map exactly the function. In this case it's uniform, but if the function has a mode, okay, if it has a point which is more frequent, it will be able to capture that also properly. Okay? And the equation in this case is simply x will be, and these are the equations programmed in the VBA, so x will be, variable x is x mean plus a random number x max minus x mean. Okay. And if I have to make the triangular, I have to make it in segments. So then I have to say the random number. First I have to find, yeah, let me just maybe copy the function from the homework. Okay, that you have for the uniform and you have for the triangle. Okay, so the triangle will have a different, because you have to make the integral in two parts. One when the curve, the line is going up, and one when the line is going down. Okay. Now that's exactly how you can also make the CPF, not the CPD, but the CPF. Okay, you can also plot it the other way. You can also make the integral from x2 to x1. Okay, let's put it here. CPF from x2 to x1, and here you have 1. Okay? And what does it mean, for example, if I say the probability here is 0? What does it mean? That I have 0 probability that x will be higher than x2. 0. If the porosity, the maximum is 0.3, I have 0. It cannot be greater than x2. Okay? If I put here a number, 50%, for example, then there is 50% probability that your porosity will be higher than this number. Okay? So be careful. It's exactly the same chart, but here is bigger. So here is smaller than that number. Okay? And here is bigger than that number. Okay? It's exactly the same integral, but one made from x1 to x2 and the other made from x2 to x1. Here, the probability of the number being smaller than x2 is 100%. Here, the probability of the number being bigger than x2 is 0. Okay? And that's exactly the distribution we use for the reserves. Okay? For reserves, we use the reverse CPF. Okay, so typically we have, and you're going to see that sometimes you see the normal distribution. We're going to see it now. You have CPF, and you have N. You have something like that. And that's 1 and that's 0. Okay. And they are, instead of simply, because it's very heavy to just to put the plot every time, right? You want to characterize your reserves or your field. So what they use is they use 3 numbers that you are probably already familiar with. They use the first number, which is 90, okay, P90 they call it. P90, okay, and P90 means there is 90% probability that N is equal or higher than P90. Okay, so I take here come with 90 or 0.9 in that case, in this case 0.9, then I knock on the curve and then I come down. That will be my NP90. Okay, NP90. I also have another famous number I use is 0.5. That's what they typically use for run production profiles, and that gives you NP50. And what does it mean? There is 50% probability that the actual N is equal or higher than P50, than that number. And I have on the most, so on the most risky, right, the most risky is 0.1, and that gives you P10. Okay, and here there is 10% probability that N is equal or higher than P10. Okay, so these 3 numbers, instead of taking the whole distribution, they simply use these 3 numbers in the business case identification, in the PDO. They sometimes use those 3 numbers. Yeah, so this one is typically called proven reserves. This one is called proven plus possible, right? And this one are proven plus possible plus what?
The second one
Is the other way, probable and probable, and then proven plus probable plus possible. So maybe they decide not to use P10, P50, and you have to find the definition, okay? Some companies use different, some companies and some countries use different percentage, okay? So in Norway, for example, 10, 50, 90. Some other country might use 5, 50, and 95. It depends. Some others use 60. So it depends from the case. So like on the Hebron field, this PDO, you can see that table. Let's see if I find it quickly. Okay, reserve estimates, you have its own section on the PDO. Okay, and you can see here they call it a bit differently. Okay, but you have for each unit, for each compartment, they call it upside volumes. That will be your P. P what? 50, 10, or 90. Okay. Which one is bigger? That we didn't check. Which one is bigger? P10. Okay. So that's one thing. The first clue is to see which one is bigger on my table. Is this one. So that's the most risky. Probably there is 5, 10, 15% that my volumes will be equal to that one or higher. Okay. Best estimates, these typically are 50 or sometimes 60. Okay. And then downside, that's P90. The ones that are sure, 90% sure, at least I have a 1 billion. I think that's 1,000, right? 1 billion. I don't think it's 1 billion barrels. Wow, it's big that field. Okay. Okay, and sometimes I have, I don't think here they provide the whole distribution because they don't want to, you have to carry with all the numbers. So it's not, people sometimes don't use it. But here there is another PDO from a field in the Mediterranean. And here you have the gas initially in place with the distribution. Okay. And you report P90, P50, and P10. Okay, let me just maybe copy that. Okay. So understood to find if we are uncertain, and this applies to any kind of process. Here we're making reserve estimation with one equation. It can be calculating NPV, can be calculating production profile, can be calculating recovery factor. So if you have some uncertainty on that input parameter, Monte Carlo simulation is a good way to compute the distribution of the output. Okay? Simply by changing it randomly. And the random number is usually made on the CPF from 0 to 1 for each variable. Some variables don't have CPF, simply they have a constant, okay? They have a number. So, so let's see here. So you always have to be careful about how this simulation, how much time does it take that function to run. Okay, in our case, we simply one equation in Excel. It happens in milliseconds. But if you are, for example, using Petrel, or you're using a reservoir simulator, maybe each simulation takes a few hours and a day. And then if you have to make 1 million, 1,000, 10,000 simulations, you're going to be forever waiting for the results. Okay, so just to put that comment here, the applicability of Monte Carlo depends on the running time of this function, okay, or it's also this simulator. Like I said here, you're going to work with one equation, so it's going to be fast. But if you have reservoir simulator, you have Eclipse, you have Petrel, maybe it takes a long time to run. Okay. So how many iterations do we need? That typically, the first procedure for that is simply trial and error. Okay. You start increasing the number of iterations until the results don't change much. Okay. So simply increase n until results don't change. Or you can use some estimate that that I'm just going to write the equation here. It's number of iterations is equal to 3 times the standard deviation of the sample divided by the error that you desired squared. And where that formula comes from, that maybe you can take it as a homework. Okay, I have tried in the past to explain, it's not very successful. Okay, so that's why I prefer to leave it to your that has a homework. Okay, but basically you have, if you were able to make infinite, okay, you have all the time of the world to make infinite samples, infinite, that will be your population, right? And then you will find the probability, the real probability of your variable, let's say n, will be something like that. Okay, of the full population, with full population. What you're making with Monte Carlo is simply you're taking part of it. 1,000, 500, 10,000, even a million. Okay, so you're taking just simply part of that population is what you're making to make your distribution, and it might be that it gives you something like that, where you have another error. Okay, so by some theorem called the central limit theorem, you can relate both by the number of points that you choose from the population. Okay? And then that's how you end up with this equation. Okay? In a very simplistic way. So if you find a nice way to explain it for your classmates in the future, your future use, that will I appreciate. But I try different things, and I think I always confuse people more than I clarify. So I decide to keep it like that. Okay. Basically, the error is how much I desire the error to be. This typically is something between 3 and 2% of the n. And I make it in terms of the average. So I take all the points I have, okay, average of the simulation points. Okay. And that's the standard deviation. Okay. And the 3 corresponds to how close you want it to be to the real distribution. And that number can be from 3 to from 3 all the way to 1. Okay, depending on the confidence, the interval confidence. Okay, but if you don't have, before trying trial and error, you run a few simulations, you find that average, and then with that you can estimate how many iterations you need. Okay, with the standard deviation of that small population and the error that you desire. Okay. Okay, what else was missing? So there are other sampling methods. Okay, there are other sampling methods that are, we will say, like smarter. Okay, they are not simply, here I'm just making random. So it will take a lot of iterations before everything is covered in a uniform way. Okay, like if I have my 2 variables, I don't see Z, but I have simply x1 and x2. Okay, if I make random, initially I might have a lot of points here or a lot of points here, but eventually if I take enough, I'm going to fill the whole area that I want to map. Okay, but might be some smarter way to make that sampling. And some other methods are called, for example, Latin Hypercube. Okay, in which the procedure is the following. I split each variable in the same number of, so I create n variables for each n will be sets for each, n subdivisions or n points, okay, n points for each variable. Okay, let's say we are going to use maybe 4, okay, so it won't be too, so I have variable 1, variable 2, and then I have here variable 1, 1, variable 1, 2, 1, 3, and 1, 4. Okay, and then I have variable 2, 1, 2, 2, 2, 3, and 2, 4. Okay, so I create a set of n points per each variable, and that will be your set like that. And these n points, n is the number of simulations. Okay, so that number usually, if Monte Carlo we say 1,000, is a bit less than that, but it has to be on that order. Okay, 500, 100, something like that. So you create a set for x1, and you create a set for x2, okay, and then you pick randomly a number in each set. That's the first step. So let's say I pick this number and this number, okay, and I run that simulation. So that will mean, in my case, what will be? It will be x1 3 and x2 2. Okay, I pick that point to make a sampling, and I run one simulation. So this will be simulation 1, will be x13 and x22. Okay, that will give you that number. Simulation 2, I pick again one of each, but cannot be the same as I already picked. That said, that number is already out. Okay, so now I pick, for example, this guy and this guy, x11 and x23. Okay. It will be these two. Then I perform. There were 4 simulations only, so I say simulation 3. That will be, for example, these two. Let me make it with this color, x12 and x21. Okay, will be here. And the last simulation, it's let's make it with which color? This color will be these two, 1,4 and 2,4. Okay, so this will be the 4 points that I use to sample my function. And if I have 500,000 points, that's the way I sample my function. Okay, it's a slightly more advanced. It's not, you are still picking a random number, but you're doing it in a predefined set, and then you're removing that number from there. Okay, and that's supposed to be to get you to the distribution faster than Monte Carlo with less iterations. Okay, and that's also typically used for reserve estimation, this method. Okay. Now, so what happens, I want to say what happens when Monte Carlo, this type of methods, okay, probabilistic stochastic sampling, takes a very long time. That makes it impractical. Or takes a very long time, is impractical. Or the other thing that can happen, I have some variables that they are not continuous. Okay, when I have non-continuous variables, when I have non okay, and that can be typically, for example, the type of offshore structure. Okay, for example, you can decide if to use FPSO, okay, a ship type, or you can decide if to use a TLP, or you can decide to use a jackup. Okay, these are things that are not continuous. It's simply a discrete variable. Okay, or if Monte Carlo takes a long time, let's say the simulation of the reserves, simulation of NPV, you have done it. You know how long time it takes. Maybe it takes you an hour. If you have to make 1,000, I make you do 1,000 iterations. You're going to be there quite a long time. Okay? So for that, we typically use probability trees are used. Okay? And probability trees, I basically try to convert the problem that I have and solve it using a number of discrete options. Okay, like for example, you have the option to develop, okay, to develop, or not developing. Okay, then if you find you want to develop, for example, then you have the squares are decision nodes. Okay, are basically something that I can decide upon. The circles are chance nodes, and I have some sort of nodes that are like that is terminal node. Okay. So for example, if you decide to develop, you might be faced with another decision, which is the type of structure, right? So you want to go maybe for FPSO, or maybe for TLP, or maybe for Jacob. Okay? And after that, you might have a chance that you're going to get the N will be high, the N will be medium, or the N will be low. Okay, so that's one. These are like they call the layers of the tree. Okay, so you have one layer which is the developing decision. Okay, layer 1. Then you have layer 2, which is the offshore structure. Then you have a third layer, which is the reserve size. And then you might have even one more layer, which is the cost. Okay, capex 1, capex 2, capex 3. Okay, but usually that's the layer 4. So that will be cost. Okay, but usually chance nodes come with a probability. Okay, it does not simply have the same probability of having n1, n2, and 3. Okay, in that case, I can say if they have the same, I can say, well, 0.33. Okay, all of them have the same chance of occurrence. I can have a big reservoir, a small reservoir, or a medium reservoir. Okay, but typically they don't have. So what happens, for example, if you use P90, P10, and P50? What probability do you assign to each one of them? So let's say, for example, if I desire, or I wish to use N1 has P10, N2 has P50, and N3 has P90. Okay, what are the probabilities associated to each option? Did you cover that in any course before? That basically, right, that question that you have, that we have here, is basically you have N and you have this CPF, okay, looking like that, and you have 3, or you have the other way, right? You have the PDF and you have your N, and it looks something like that, and you want to make it, you have here P10, 90, P50, and P10, and you want to convert it from a continuous distribution to a discrete distribution. Okay, so how do I do that? I basically don't want to use the full, I cannot run Monte Carlo because it takes a long time, so I want to make it like that. Okay, I want to make evaluate on the tree, but I have to assign a probability of occurrence for each case. Okay, and let's say I want to work with the same numbers, 10, 50, and 90. So I want to find, instead of using this chart, I want to use 3 options, each one with a probability. Okay, so one way I think it's nice if we make it graphically. Okay, so one way I define here P, that will be 90, right? So what I try to say, I try to locate the difference between 1 and this number. That difference will be the probability of P90. of NP90. Okay, but I have to locate that marker exactly when this area and this area, sorry, the opposite, this area and this area are the same. So I have to move that line, this red line, up and down until these two areas are the same. Okay? And that will give you, so that will be, let's call it this location. How do we call that location? X. X should be placed such that, let's change the color. Okay, such that this area and this area are the same. Okay, which is equivalent if you integrate the area under the curve. To integrate, you have a lower bound, but to define the upper bound such that the mean value of that interval is exactly P90. Okay, but I prefer to show like the graphical instead of doing it with equations. Okay, so I try to find exactly X such as these two areas are the same. Then I have P50 here, and then I try to define this X1 in the same way. Okay, such that I come here, knock the curve. Let's put it in blue maybe. Such that these two areas, this area and this area, are the same. Okay? Because if the two areas on each side are the same, that means that that's the mode of that interval. That's the most likely value on that interval. Okay? So now after I have each option, right, I reach here to an end node. Okay, these are all the capex, but let's put it like that. So how I'm going to evaluate, for example, to compare each one of these options, FPSO, TLP, or Jacob. How I'm going to know which one should I choose? Or how should I say, how should I compare develop or non-develop? This is easier, right? Non-develop has simply a value, monetary value of 0. I don't make money, but I don't lose money. Okay? How do I find the value of this branch? Or how do I find the value of this branch? Okay, so you have to calculate the cost for each option. So how many options we have here? So you have to make options. Okay, so you have option number. Let's make it maybe here. Okay, let's say this option. Okay, this option that I have here. This option has what combination? FPSO, right? Then it has N3, okay, and then it has capex 1. These three options, okay. So what I use, I say the monetary value, okay. I calculate the expected monetary value. Okay, that can be, for example, using NPV of that option. But you also calculate the probability of that option. Okay, and the probability of that option is the probability of that option of the option is, in that case, will be the probability of N3 times the probability of capex 1. Okay, so for example, if these are 3, 3, all of them have the same occurrence, then you end up with 0.33 times 0.33.
Shouldn't be the percentage
Well, actually, there is no percentage. That's something I'm deciding. Okay, so square nodes, decision nodes have no probability. That's something I decide. I am the field designer. While these ones, I'm by nature. Simply nature can give me a big reservoir, can give me a small reservoir or a medium reservoir. So that's where I need, is very important, that probability. So then you can say this option has this value, but that option has this probability of occurrence on the whole tree. Okay? Now, how do I compute the probability of the branch? Let's say the FPSO. I want to compare how profitable FPSO is compared to TLP. Okay, to calculate the monetary value or the expected monetary value of a branch, then you have to make the sum from I equal 1 to n of the probability and the expected monetary value of all the options on that branch. Okay, of all options on that branch. Okay, like in our example here, we have how many options we have? We have 9. Okay, 3 different reserve sizes and 3 different capex. So we're going to have 3 times 3, 9. Each one will have a probability, each one will have an expected value, and with that, then you multiply the probability of each case with the value of each case, and that gives you the expected monetary value of the branch. Okay? And with that, you can compare the 3. The FPSO gives you a number, maybe it's higher than the TLP. Now, what happens if I want to compare developing or not developing? I do the same, but now I have to sum all of them that are on that branch. Okay? And in that case, I don't need to add probability because that's a decision node. Okay, simply I just add all of them up. Okay? Yes. So we arrived, that's the end of the lecture. So let's see, try to make, were a few things, okay, we covered today. So first we went to how do we characterize uncertainty on the input variable, okay, for any simulation, equation, anything. We have measurements. We simply make the frequency analysis, that's called frequency analysis. And then we find the probability distribution. If we have enough samples, we can say what we measure, what we haven't measured will behave in the same way that what we have measured. Okay? That means that for the whole field, the probability will be the same. If I have, on the other hand, no idea or no data, I can use some distributions according to experience or simply, because I don't have those numbers. Then, because all the input to that function has uncertainty, has a distribution, then the output probably will have a distribution. Okay? To calculate that, I have to use a sampling method. And one of the methods which are most commonly used, because they're very simple to use, is Monte Carlo, in which I take a random sample here for all of them, I run the simulation, and I calculate the number. Then I take another random number, run the simulation, and calculate another number. And then at the end, I make a frequency analysis on the output, and I find the distribution. How many simulations to use? You have simply to increase until you see that the results don't change. The random number is typically chosen on the CPF, the cumulative distribution function. simply because it's, you have simplest number between 0 and 1. So it's much simpler to pick from there. For reserves, we use this CPF also. We have P90, 50, and 10. We could also have some other numbers. Number of iterations, as I told you, you try increase until the results don't change. Or you can use this estimate that assumes that both distributions are normal distributions. Okay, you take for the whole population, you don't know, but they are related somehow by the number of iterations, the number of samples that I take. That's a small comment on Latin Hypercube, another method to try to make the sampling more efficient. Usually takes less iterations than Monte Carlo. And how do we deal with decision variables? Or how do we deal if each simulation takes a long time? For example, here, we maybe to calculate the economic calculation, okay, we will have to make again 10,000 simulations of NPV. Change the number, change the rate of the field, run the production profile, and then calculate NPV. That might take you like half an hour, okay? Me like 1 hour. Okay? So you decide to choose not to run all cases, but then just choose only a few cases. Here you will have to run only 9 instead of 1,000, okay? But it's very important to assign a probability of each branch of occurrence. And that you do with the continuous distribution, and you discretize in you try to make that the area will be the same in both sides, and that will be the probability. Okay? And then to compare branches, you simply calculate the weighted value times the weighted probability times the value. Okay? Any question before we close? So tomorrow you're going to have an exercise session. I might come, I'm not sure yet. But you're going to have an exercise session with Anga, where you're going to practice this the Monte Carlo part. Okay, see you tomorrow.